Hi everyone, this is Maverick Paul, the chemistry guru. Now we want to move on to the second portion involving the suggested solutions for 2022 A-Levels H2 Chemistry Paper 1. So let us take a look at question 11. Now question 11 for the reaction NH4NO3 to give me N2O plus 2 water. Enthalpy change of the reaction is given minus 124 kJ per mole. Which of the statement is correct? Question is asking about spontaneity of the reaction, whether it is at high temperature, low temperature, and so on. So let us run through the concept and we determine at which temperature will the reaction be spontaneous. Now the topic tested in this question obviously is under energetics involving Gibbs free energy. And what we will have to determine first is we have to determine the entropy change of the process. Now, entropy change is a measure of the degree of disorder. So based on the differences in the physical state between the reactant and the product, I should be able to determine whether is there an increase in the degree of disorder or a decrease in the degree of disorder. Then we can link it to delta S or your entropy change. So involving my reactant, this is a solid. Involving my product, I have N2O, which is a gas. Water, it is a liquid. So usually when we have gaseous species involved, then we will only focus on changes in the moles of gas because entropy for gases will be the most significant. And therefore, I only need to focus the change in entropy based on the change in the moles of gas. Since there is an increase in the moles of gas from 0 to 1, I will expect there's an increase in the degree of disorder. So delta S for this equation will expect it to be a positive term. Delta S will be a positive value. Involving delta H, we already have this information given in the question. This is a negative value. So I have the sign of delta H, I have the sign of delta S. We will be able to sub this into your Gibbs free energy equation. Delta G equals to delta H minus T delta S. From there, I can decide at which temperature will my delta G be negative. So what we do is sign of delta H, it is negative. Sign of delta S, it is positive. Then we will consider what is the sign for minus T delta S term. Since delta S is positive, minus T delta S will be a negative term since temperature in Kelvin will always be a positive value. Delta S positive minus T delta S will have to be a negative term. So you notice my delta G is made up of these two terms, delta H, which is always negative, minus T delta S, which is also negative. When you add up these two negative terms, your delta G will always be negative, which means that the reaction will always be feasible. So answer to this question is fairly simple. It will be option D, reaction is spontaneous at any temperature. Now question 12, we have hydrogen peroxide slowly decomposes at room temperature. The equation is given. Two experiments are performed to study the effects of adding lead-4 oxide on decomposition of 1.5 mole per dm cube hydrogen peroxide at the same temperature. Experiment 1, you're using 20 cm cube of hydrogen peroxide. Experiment 2, you're using the same volume of your hydrogen peroxide at the same concentration, but now you throw in 1.0 gram of lead-4 oxide. At the end of experiment 2, mixture was filtered and you will end up getting back 1.0 gram of lead-4 oxide, which is suggesting to us that it is not taking part in the reaction, it is chemically unchanged at the end of the reaction. Now the graph that we have is something like this. Actually, we will expect that there is a difference in the rate of the reaction involving experiment 1 and 2. So we will analyze this in a while. Which row is correct? Talking about the value for rate constant for experiments 1 and 2 and activation energy for experiments 1 and 2. Now, the topic tested in this question obviously is under kinetics. And since involving experiment 2, when you put in 1 gram of lead-4 oxide, at the end of the reaction, we are recovering back the same mass of lead-4 oxide. This will suggest that your PbO2, it is a catalyst. It should increase the rate of the reaction. And you notice if you consider the volume of O2 that we can collect versus the time taken, the rate of formation of your O2, which is the product, is way faster. So this is suggesting that yes, your reaction is catalyzed. Your PbO2, it is a catalyst. Experiment 2, it is catalyzed. Experiment 1, it is not catalyzed, and the catalyst obviously will be my PbO2. And if I compare my rate constant versus my activation energy, If it is a catalyzed reaction, obviously the rate constant is going to be a bigger value for experiment 2. And the reason why the rate constant for experiment 2 is bigger, for catalyzed reaction, what the catalyst is doing is it is providing an alternative reaction path with a lower activation energy. So when the activation energy is lower, it's easier for the reaction to occur. So we will expect activation energy for the catalyzed reaction to be lower. Remember, activation energy is like the energy barrier that the reactant need to overcome to proceed to form product. Lower activation energy, then you have more reactants, easier for it to proceed to form product, and it means that the rate of the reaction will be faster. So we will expect for experiment 2, rate constant bigger, activation energy smaller. So in this case, answer to this question will be option C, higher rate constant for experiment 2, higher activation energy for experiment 1. Question 13, reaction between sulfur dioxide and oxygen is reversible. Equation is given here. 2 moles of sulfur dioxide, 2 moles of O2, placed in a vessel of volume 0.500 dm cube and allowed to reach equilibrium. At equilibrium, we have 1.80 moles of sulfur trioxide present. What is the value for Kc under the conditions used? Now, the topic tested in this question obviously is under chemical equilibria. We are given information for me to fill up the ice table. Moles of SO2 is 2. Moles of O2 at the beginning is also 2. At the beginning, usually we will assume that there's no product form. SO3 at the beginning is 0. Then what we also have is, at equilibrium, question tells me that I have 1.80 mole of SO3 at equilibrium. So this means that the change in the number of mole of SO3 will be plus 1.8 from 0 to 1.8. This is a plus 1.80 moles. And if I have this change in SO3, which is plus 1.8, then what I can do is I can fill up this entire change row. This change row will follow the mole ratio of the balance equation. The balance equation says that 2 moles of SO2 will react with 1 mole of O2 to give me 2 moles of SO3. 2 is to 1 is to 2. So the change row will also follow mole ratio of the balance equation. The mole ratio for my change row will also be 2 is to 1 is to 2. This is 1.8. The change in the number of mole of SO2 will also be 1.8, and the change in the number of mole of O2 will be 0.9. Mole ratio is 2 is to 1 is to 2, 1.8 is to 0.9 is to 1.8. Reactant is going to be used up. These two guys are negative sign. Product it is formed, this is a plus sign. I just add the two rows together. I'll have the equilibrium number of mole of SO2, which is 0.2, O2, which is 1.1, SO3, which is 1.8. So I have the number of moles of each of these species at equilibrium. We have to keep in mind when we sub this into my Kc expression. Kc is in terms of concentration, and since the volume of the vessel is given, I'll have to divide all this number of moles by the volume to get a concentration, which is the volume is 0.5 dm cube. The concentration for each one of them at equilibrium 0.4, 2.2, and 3.60 mole per dm cube. So once we have that, I can write out my Kc expression. Remember, Kc is the concentration of the product divided by the concentration of the reactant raised to the power of the coefficient. So my Kc will be SO3 concentration square divided by SO2 concentration square and O2 concentration. I have all these values. I can substitute. SO3 concentration is 3.6, which is here, the numerator. Your SO2 concentration is 0.4, which is here, 0.4 square. And your O2 concentration, 2.2, which is here. And I'll be able to calculate my Kc expression, which will work out to be 36.8. So the value for Kc is 36.8. Answer to this question will be option B. Now, question 14, I have a hydrogen carbonate buffer solution used to maintain an almost constant pH in blood. The equilibrium that applies to this buffer solution is here. H2CO3 to give me HCO3 minus plus H plus. K value is also given. pH is maintained at 7.4. And what is the ratio for H2CO3 to HCO3 minus that gives me this pH of 7.4? Now, obviously, this is a buffer solution. So topic tested will be involving buffer solution under equilibria. And involving a buffer is a solution that can maintain pH when you're adding small amounts of H plus, small amounts of OH minus. So usually what I like to do is I like to use this diagram to help us visualize what is a buffer. A buffer is made up of essentially two things. Since it can maintain pH, I need to have acid present that can remove OH minus. In this case, inside this buffering system in blood, my acid is H2CO3. The job of this H2CO3 is to remove OH minus. And I also need to have a base, and the buffering system for this blood, the base will be my HCO3 minus. The job of your HCO3 minus is to remove H plus. I have an acid that can remove OH minus. I have a base that can remove H plus. And this is how your buffer solution can maintain pH. It's essentially a mixture of a conjugate acid-base pair. Now, these two guys, they can coexist with each other because they are a conjugate acid-base pair. When they undergo acid-base reaction, they will just be converted to and from each other. H2CO3, when it reacts with OH minus, it will form HCO3 minus. HCO3 minus, when it reacts with H plus, it will form back H2CO3. So this special mixture of acid and base, they can exist together in the same equilibrium, and therefore this special mixture, a mixture of a conjugate acid-base pair, is capable of maintaining pH. Essentially, we know that this guy is a buffer, and we know that I have to use the buffer equation, and since the pH is given, so what we can do is we can just find the ratio for the concentration of your salt to acid. Buffer equation, usually we will use this expression, pH is equals to pKa plus log salt concentration divided by acid concentration. Some of us will use conjugate base versus acid concentration, but whichever expression that we're using, we should be able to recognize that the acid is H2CO3, the salt or the conjugate base will be HCO3 minus. So this ratio, HCO3 minus is on top, H2CO3 is at the bottom. It's a little bit different. It is the inverse of what we have in the question. So later, whatever that we determine, we need to inverse that value. But let us work towards finding this ratio first. Now, involving the pH is 7.4, pKa value is just minus log Ka value, which is already given in the question, plus log HCO3 minus over H2CO3. Next thing we do is we just try to do some rearrangement. I want to figure out what is my log HCO3 minus over H2CO3 expression, which is 7.4 plus log 2.5 times 10 minus 4. This will work out to be 3.797. Then I can remove the log term. This ratio, HCO3 minus over H2CO3, is equals to 10 to the power of 3.797. This value is 6266. And remember what the question one is the inverse of it. I want H2CO3 to be in the numerator, HCO3 minus in the denominator. So basically what I have is I just have to inverse that guy, 1 divided by 6266. This will give me 1.59 times 10 to the power of minus 4. So we'll figure out this ratio, and if I look through the options, answer in this case will be B, 1.6 times 10 to the power of minus 4. Now question 15, I have an excess of silver chloride added to water. Make sure it's shaken until equilibrium is reached. So how is the solubility of silver chloride in this equilibrium mixture affected by addition of ammonia, sodium chloride? So I have 4 possible options involving what happens when you add ammonia, what happens when you add sodium chloride, how is the solubility affected. Now, the topic tested in this question is under solubility product. Actually, it's targeting the common ion effect and is related to that. Involving the dissociation of a sparingly soluble salt, we know that AgCl, solid, since it is sparingly soluble, it will be partially dissociated to give me Ag plus equals Cl minus equals. This dissociation is easy. Now what happens when you add ammonia? When you add ammonia, what happens is your Ag plus will undergo complex formation to form your diamine silver complex. And the formula involving your diamine silver complex is here. And what this means is you are decreasing the concentration of your cation, concentration of Ag plus equals, which is essentially Ag plus surrounded by water. And when you're forming this diamine silver complex, you're forming a different complex, and the concentration for Ag plus equals Ag plus surrounded by water. The concentration decreases, and this decrease in the concentration of my product will trigger the position of equilibrium to shift towards the right hand side to dissociate more, to release more Ag plus equals. So basically this is just Le Chatelier's principle. When you have a decrease in the concentration of the product, POE will shift towards the right hand side, favor the formation of my product. Actually, this will also trigger more of the salt to dissolve, and therefore the solubility for the salt will increase. Now actually we see this in QA. When we do practical involving QA, if I have a solution involving chloride, what we will do is we will add AgNO3 to precipitate the silver chloride, and when we add ammonia, we will expect silver chloride to dissolve. For the same reason, When you add ammonia, you form this diamine silver complex. Concentration of your Ag plus decreases. You trigger the AgCl to dissolve, and therefore, when you add ammonia, your AgCl precipitate will dissolve. Based on this idea here, solubility for AgCl increases since more of the salt dissolve. So in this case, involving adding ammonia, we will expect solubility to go up, solubility to increase. Now, involving the second one, which is a lot more straightforward, this is purely based on my common ion effect. If I'm adding sodium chloride, which is soluble, the concentration of Cl- will go up. If I'm increasing concentration of my product, then position of equilibrium will shift towards the left-hand side, and this means that less of the salt will dissolve, solubility will decrease, or solubility is suppressed. So we understand involving your common ion effect, in the presence of a common ion, solubility of a sparingly soluble salt will be suppressed, solubility will come down. So we already have determined what will happen to solubility. When you're adding ammonia, we expect solubility to go up. Solubility when you're adding sodium chloride, a common ion, we expect solubility to decrease. So answer in this case will be option C. Now question 16, another question involving solubility product, excess of silver sulfate, Ag2SO4 shaken with water at equilibrium, silver ion concentration is 0.032 mol per dm cube. Question is asking for silver ion concentration when excess of Ag2SO4 is now shaken with 0.5 mol per dm cube of sodium sulfate. Sodium sulfate is soluble, sodium salts are soluble. I have 4 options, and of course we want to determine the Ag plus concentration in the second scenario. Now, what we will have to figure out first is the KSP for our silver sulfate. Given your saturated solution, since it is at equilibrium, your Ag plus ion, 0.032 mol per dm cube, when the system is at equilibrium for a sparingly soluble salt, it means that the solution is saturated, solution is hanging on to the maximum amount of ions that it can handle. So system is at equilibrium, and therefore when system is at equilibrium, I can link it to KSP, equilibrium constant. And since my Ag plus concentration is 0.032 for a saturated solution, then if I consider the dissociation involving Ag2SO4 to give me 2 Ag plus and 1 SO4 2 minus, concentration of Ag plus is 0.032. Remember, involving the dissociation of the salt, one salt will give me 2 Ag plus and 1 SO4 2 minus. If X is the solubility for your silver sulfate, then X will give me 2x concentration of Ag plus and X concentration of SO4 2 minus. And question tells me Ag plus concentration 0.032, and this is effectively 2x because your 1 mole of your salt will give me 2 moles of Ag plus. X concentration, solubility of my salt, will give me 2x concentration of Ag plus. So this is 2x. And therefore, I know that concentration for sulfate will be, comparing mole ratio, will be half of it, which is X, 0.016. So I know that the concentration of Ag plus at equilibrium is 0.032, 2x, and the concentration for sulfate will be 0.016, which is X. And therefore, I can sub this into my KSP expression. KSP is Ag plus concentration square multiplied by sulfate concentration. Plug in the values, 0.032 for concentration for Ag plus, 0.016 for concentration for sulfate. Then my KSP will be 1.638 times 10 to the power of minus 5. So first thing we got to do is we have to determine KSP. Then we consider this same KSP value for the second scenario. What if the solution now is in 0.5 mol per dm cube of sodium sulfate? Scenario number 2. Now scenario number 2 is actually a common ion effect question, but it's a calculation based question. Now what happens to solubility for your same salt, Ag2SO4, with the same KSP value? KSP value is the same guy here, but now I throw this guy into 0.50 mol per dm cube of sodium sulfate. I have 2 dissociations because I have 2 salts. We have to consider each one of them. Silver sulfate is going to give me 2 Ag plus SO4 2 minus. The dissociation is the same, but solubility will be different. I'm going to write this as y is to 2y is to y, and it will be a different value as compared to the previous one that we have determined. This y value will be different from x. Because x is solubility in water, y is solubility for Ag2CO3 in the presence of a common ion, 0.50 mol per dm cube of sodium sulfate. Now sodium sulfate concentration is 0.5. It's going to give me 2 Na plus and 1 SO4 2 minus. Na plus concentration is not important, we're just going to ignore that. Sulfate concentration that comes from sodium sulfate is 0.5. Hopefully we notice that both of them is dissociating to give me sulfate, and so therefore I have a common ion here, and I have two sources of SO4 2 minus. So the concept involving common ion effect actually should come out. Since I have a common ion, I know that the solubility for sparingly soluble salt will be suppressed, and we will expect the value for Y to be a smaller value than what we have calculated previously, or what is given previously, 0.016. Correct? The concept has to be there. Now, calculation wise, I will write down the KSP expression involving Ag plus concentration squared and sulfate concentration. Ag plus concentration, all the Ag plus comes from the sparingly soluble salt, which is 2Y. We're going to put this here, 2Y squared. Sulfate concentration, now I have two sources of sulfate. Y that comes from AgSO4, Ag2SO4, and I have sulfate concentration that comes from sodium sulfate, which is 0.5. I can add them together. This is 0.5 plus Y, since I have two sources of SO4 2 minus. The next thing we notice is this equation is a quadratic equation. In syllabus, we do not solve quadratic equation. When we see quadratic equation, instinctively we have to impose an approximation. The approximation is fairly simple. We just say that, hey, since this is a sparingly soluble salt, the dissociation involving my sulfate from the sparingly soluble salt is not important. Y is a very small value, so we're just going to assume that all the sulfate just come from the fully soluble salt. 0.5 plus Y will just be roughly equals to 0.5. Now, some of us might impose this approximation before substituting this value into my KSP term, but it is the same approximation, and the reason for this approximation is to avoid solving for quadratic equation, because solving quadratic equation is not a syllabus. So if I encounter quadratic equation, I'll have to impose the approximation, otherwise we will not be able to calculate this guy, correct? So what we will do is we will approximate, okay, this sulfate concentration is roughly equals to 0.5. KSP I've calculated previously, my Y term is here. I'll have an equation involving Y. So solve for Y. Y would work out to be 2.86 times 10 to the power of minus 3. Now this is not the answer. We have to be very careful with this, because when you look back at the option, my Y is not my Ag plus concentration, because the question is asking for Ag plus concentration and the Y, which is solubility for your salt. It actually gives me 2Y concentration of Ag plus. Therefore, I need to double this value. Ag plus concentration is 2Y, 2 times solubility, basically. It will be 5.72 times 10 to the power of minus 3. So answer in this case to this question will be option C. Question 17, which reaction steps result in the formation of a carbocation, carbon which is positively charged? Now, I have 4 arrow pushing involving 1, 2, 3, 4. So we just need to figure out for each one of them which one will give me a carbocation. Now the topic tested in this question is under organic chem, a little bit related to mechanism, because we need to interpret the arrow pushing. Involving step number 1, what we have is a homolytic fusion. You have a carbon radical combining with a chlorine radical. What we end up with will just be a CCl bond. The product should be neutral. There's no carbocation. Number 1 is not my answer. Now number 2, what I have is I have a CCl bond. This is a full arrow. So therefore this guy is a heterolytic fission. You're breaking this bond unequally. 2 electrons go to this chlorine. End up Cl will be a -1 charge and the carbon will be a plus charge. So this guy will give me a carbocation. Step number 2, it is part of the answer. How about number 3? Number 3, I have a carbon bonded to a O plus. Because this oxygen is bonded to 2 additional hydrogen, oxygen carries a positive charge. Now, same idea, if I draw a full arrow, which shows the movement of 2 electrons, point from my CO bond, point to oxygen. Basically, I'm giving 2 electrons to oxygen. O plus will gain the electron and become O neutral. So basically, this is just water, and carbon will become positively charged, and this will be my carbocation. Equation number 3, or step number 3, I'll also form a carbocation. So number 3 is also part of the answer. Finally, involving number 4, what I have is I have O minus. I draw an arrow from the lone pair of my O minus, point to between this carbon and oxygen. Basically, I'm forming a double bond, or forming a pi bond. Then later, what I'll do is I'll draw a full arrow from my CCl bond. Both electrons go to chlorine. I'm breaking this CCl bond, both electrons go to chlorine. This Cl will be a minus. Cl will be a minus charge. Oxygen will be neutral because O minus giving electron, it will become neutral. Then chlorine from Cl neutral receives electron, it will form Cl minus. If I look at carbon, carbon is neutral at the beginning. It gains electron from your oxygen, but it loses electron to chlorine. So there's no net gain or loss of charges. My carbon will remain neutral. In this case, this carbon will remain neutral. I will not be able to get a carbocation. So in this case, it's fairly simple. Only number 2 and number 3 will give me a carbocation. Answer to this question will be A. Question 18, we have this drug, ibuprofen, has 2 enantiomers. One enantiomer has the desired activity, while the other one is inactive. It doesn't do anything. Which statement gives correct reasons for the difference? Number 1, biological receptors that the drug bonds with are chiral. Number 2, enantiomers are structural isomers with different chemical properties. Number 3, the enantiomers have many different physical properties. Which of this statement is valid? Now, since we're talking about optical isomers or enantiomers, then by right topic tested in this question is Intro to Organic Chem. Now in syllabus, we actually don't differentiate between the chemical properties for stereoisomers. That means cis-trans isomer, we will assume that there's no difference in reactivity. Your optical isomers, which comes from a chiral carbon, we will assume that there's no difference in reactivity, because if I consider the reagents and conditions that we have in syllabus, we do not have chiral species. All the reagents and conditions are achiral, or they do not have stereochemistry, and therefore we will not be able to use reagents and conditions in syllabus to try to differentiate between optical isomers, between cis-trans isomers. Actually, they do have differences in reactivity, but only when they are reacting with chiral species, only when they are reacting with compounds that also have optical activity. So involving statement number 1, biological receptors that the drug bonds with are chiral, this is valid. Involving optical isomers, we can only bring out the differences in their reactivity only when it is reacting with chiral compounds with optical activity. So statement number 1 is valid. Now number 2, enantiomers are structural isomers with different chemical properties. This is wrong. They have different chemical properties, but they're actually not structural isomer. Enantiomers are stereoisomers, correct? Stereoisomers, they have the same molecular formula, they have the same structural formula, but the arrangement of the groups in space is different. So therefore, they're still isomers of each other. Essentially, they're still different compounds. And again, in this case, statement number 2 is not true, because your enantiomers, they are not structural isomers. Structural isomers, they'll have different structural formula, which is not true. They are stereoisomers, they are not structural isomers. So number 2 is wrong. Number 3, enantiomers have many different physical properties, which again is not true. Optical isomers or enantiomers, they are virtually identical physical properties. There's only one physical property that is different, which is its optical activity. Optical activity is the ability for your chiral species to rotate plane polarized light. So involving my optical isomers, we know that we have the plus isomer and the minus isomer. The plus isomer can rotate light clockwise, minus isomer can rotate light counterclockwise. It means that there's only one physical property that is different, which is the optical activity for your enantiomers. Otherwise, the rest of the physical property, they are essentially the same, including melting point, boiling point, density, and so on. All right. So in this case, only statement number 1 is valid. Answer to this question will be C. Now, question 19, we have allyl alcohol. The compound is here. Can be converted to propanol by using a catalyst containing a ruthenium complex. So the equation is here. Which type of reaction is the overall process? Is it hydrogenation, isomerization, which is something that we never encountered before, not really in syllabus, so we have to try to figure out, is it oxidation, is it reduction? Now, actually topic tested in this question is under Intro to Organic Chem, talking about all the different types of reactions that we have. And if I consider the differences between the reactant and the product, basically what we are doing is actually we are doing 2 different things. We are converting my alkene to alkane. I'm adding hydrogen to my alkene. And what I'm also doing is I'm converting the alcohol to a carbonyl compound, to an aldehyde functional group. So it looks like I'm doing 2 different things. I'm adding hydrogen to alkene, removing hydrogen from your alcohol. So is it hydrogenation? Hydrogenation is when you're adding hydrogen. So it's actually not entirely true, because I'm adding hydrogen to my alkene, but I'm removing hydrogen from my alcohol. So number one is maybe not so good because it's not just purely adding hydrogen. I'm also removing hydrogen from another functional group. Now, is it oxidation? Oxidation, I'm either losing hydrogen or gaining oxygen. Again, you notice it's actually a mixture of two things, because if I'm adding hydrogen to my alkene, basically I'm reducing the alkene. If I'm removing hydrogen from my alcohol, basically I'm oxidizing my alcohol. So it's like a combination of oxidation and reduction. So statement C and D, both of them are problematic. It's not really oxidation because there's also reduction. It's not only reduction because there's also oxidation. Option C and D is also not a very good answer. Now, involving B in this case, which is pretty interesting because we never encountered this before, but B will be my best answer. We just call this isomerization. Isomerization just basically means that I'm forming another isomer of itself. And if you think about it, when you add 2 hydrogen to alkene and when you remove 2 hydrogen from your alcohol, basically you're just shifting the position of hydrogen from one functional group to another functional group, and the total number of carbon, hydrogen, and oxygen between these two guys are effectively the same. We end up involving the product, differences between my product and my reactant. They end up having the same molecular formula, but the functional group is different. So saying that this is isomerization is actually the best answer in this case, and therefore answer in this case will be option B. Now question 20, some of the defensive odors secreted by termites have a structure similar to sembrine A as shown. So this compound here, there's a lot of double bond present. This guy is treated with an excess of hydrogen gas over a platinum catalyst. Basically, it's just reduction. And involving the product, we want to determine how many chiral centers are formed inside this reaction. This is fairly simple. Topic tested is under Intro to Organic Chem, trying to find the number of chiral carbon in the product. So what we will have to do is, first thing is I have to try to identify, okay, if I were to reduce this guy, how many chiral carbons I have in the product. First thing we will have to do is I have to try to figure out the product. Of course, what we can do is we just modify whatever diagram that is given in the question, but what I've done is I try to draw the product properly, so it's a little bit clearer. And if you look at the cycle compound, we actually have quite a number of carbon. To make it easier for comparison, I've numbered my carbon. Of course, there's no need for us to do that. In the question, you notice when you're adding hydrogen in platinum catalyst, you're just reducing my alkene to alkene. And on adding hydrogen, my product will be something like this. And the next thing we do is we just look out for a chiral carbon bonded to 4 different groups. Carbon position 1 is chiral because it's bonded to CH3, hydrogen, and 2 different groups. So carbon position 1 is chiral. Carbon position 5 is also chiral. Carbon position 9 and carbon position 12, they're all chiral. So basically, chiral carbon is just carbon bonded to 4 different groups. We should be able to identify each one of them. And I'll have just 4 chiral carbons here. So answer to this question, very, very simple exercise, will just be option D.